Sequences. We'll start with a definition. A sequence is a list of numbers written in a definite order. We'll often use a sub 1, a sub 2 through a sub n, and it continues on to describe a sequence. And so the sequence, with the set containing a1, a2 through and up to whenever, can be denoted by the set containing a sub n, or the set containing a sub n from n equals 1 to infinity. All right, so we will often be discussing what are called infinite sequences, and so we will sort of make the assumption that the sequence goes on to infinity unless we're told otherwise. So here we're asked to list the first 5 terms of the sequence if we are told that a sub n is described as the cosine of n pi over 2. All right, so we make the assumption that n starts at 1. So then a sub 1 would equal the cosine of 1 pi over 2. And the cosine of pi over 2 is 0. A sub 2 would be the cosine of 2 pi over 2, which is pi, and the cosine of pi is negative 1. A sub 3 would be the cosine of 3 pi over 2. The cosine of 3 pi over 2 is 0. A sub 4 would be the cosine of 4 pi over 2. That's the cosine of 2 pi, which is 1. And let's see, a sub 5 would be the cosine of 5 pi over 2. And 5 pi over 2 is equivalent to pi over 2. And so the cosine of pi over 2 is 0. And so we would say that we would have what? 0, negative 1, 0, 1, 0, and so on. And there's the first 5 terms of the sequence. Suppose a sub n is described as negative 1 raised to the nth power times n over n factorial plus 1. Now, if you aren't familiar with this notation, the factorial notation, n factorial is equal to 1 times 2 times 3 times 4 times n minus 1 times n. And we say that 0 factorial is equal to 1. All right, so that's what that notation means. We call that factorial. All right, so a sub 1 would be negative 1 to the first power times 1 over 1 factorial plus 1. Negative 1 to the first is negative 1 times 1 is negative 1. 1 factorial is 1 plus 1 is 2, and so that would be negative 1/2. A sub 2, that would be negative 1 to the second power times 2 over 2 factorial plus 1. So that would be 1 times 2, which is 2, over 2 factorial. 2 factorial is 1 times 2, which is 2, plus 1 is 3. A sub 3, negative 1 cubed times 1. I'm sorry, that would be times 3. Over 3 factorial plus 1. So that would be negative 3 over 3 factorial is 1 times 2 times 3, which is 6, and 6 plus 1 is 7. Negative 3/7. A sub 4, negative 1 to the 4th times 4 over 4 factorial plus 1. So that would be positive 4 over 4 factorial is 1 times 2 times 3 times 4. So that's 6 times 4, that's 24, plus 1 is 25. And one more, a sub 5, that would be negative 1 to the 5th times 5 over 5 factorial plus 1. So that would be negative 5 over 5 factorial is 1 times 2 times 3 times 4 times 5. That's 120 plus 1. It's 121. All right, so our Our set would be what? Negative 1/2, 2/3, negative 3/7, 4/25, negative 5 over 121, and so on. Notice that this is an alternating sequence. Alternating because notice the signs change each time. Okay, we've also learned about the factorial notation. That's an important notation. We're going to be using that frequently in later sections. So now let's kind of turn the idea around. Let's start with the sequence and determine a formula for a general term of the sequence, if we assume that the pattern of the first few terms continues. So here we see the sequence 5, 8, 11, 14, 17, and so on. Now I look at this and I see a linear pattern. Right? We could maybe describe a linear function based on this, and if we were in an algebra course. All right, so what I see is each time we're adding 3. And so we can sort of say, that's sort of a slope concept. All right, so the slope, the change is 3. And so we might start by saying, well, a sub n is 3n plus something. And then we just have to make it work. And so remember, this is n equals 1, and this is n equals 2. And so if n equals 1, 3 times 1 is 3 plus what gives me 5? 3n plus 2. So a sub n is 3n plus 2. And we can verify this with the other terms. For example, if n equals 4, we're supposed to get 14. 3 times 4 is 12 plus 2 is 14. So that works. All right, let's look at the next exercise. Here we have the set containing 3/16, 4/25, 5/36, and 6/49, and so on. All right, and so if I look at this, I immediately notice that in the denominator, those are perfect squares, right? 16 is 4 square, 25 is 5 square, 6 square, 7 square, and in the numerator I see a linear pattern, right? 3 plus 1 is 4, plus 1 is 5, plus 1 is 6. Now we need to describe these in terms of n, and remember that this is the n equals 1 term, n equals 2 term, n equals 3 term, n equals 4 term. All right, so notice, how can I get, if I look at the denominators, how can I get from 1 to 4? How can I get from 2 to 5? From 3 to 6? From 4 to 7? Well, each time I'm taking the n and increasing it by 3 and then squaring, and that gives me the denominator. Now in the numerator, since the change is 1 each time, I know I have an n plus something. All right, and remember this is the n equals 1 term. 1 plus what gives me 3? 1 plus 2 gives me 3. So a sub n is n plus 2 over n plus 3 squared. And we can check that with any of the other terms. All right, so it's really just trying to figure out the pattern based on the nth term. When talking about a sequence, we will want to know if the sequence converges or diverges. And what we mean by that is, if a sequence, a sub n, if it has some limit L, and we can write the limit as n approaches infinity of a sub n equals L. If the terms of the sequence approach L as n gets larger. If that happens, we say the sequence converges to that L. If the sequence does not converge, it diverges. All right, so if we see the terms of the sequence approaching some number, we say that the sequence converges to that number, and we call that number L. All right, now related to that, it says that if the limit of, as x approaches infinity, of some function is L, and f of n is equal to a sub n, where n is an integer, then the limit of a sub n is L. What that means is, we are allowed to find a limit at infinity for a sequence like we would a function. We basically take the sequence and change it over to function notation, evaluate the limit like we would using the techniques we've learned, and if we find that that limit exists and is a specific value, a non-infinite value, then we can say that the sequence converges. Related to that, if under absolute value the limit of the sequence is 0, then the limit of the sequence without absolute value is also 0. And that we'll be able to use when we're talking about sequences that are alternating. We'll be able to use that theorem. Alright, so let's see some examples, determine whether some sequences converge or diverge. Alright, so determine whether the sequence converges or diverges. If it converges, find the limit. Alright, so if a sub n is given as 4 times the square root of n, to determine if the sequence converges or diverges, what I can do is I can think of the related function f of x is equal to 4 times the square root of x. And I can take the limit as x approaches infinity of 4 times the square root of x. Well, as x approaches infinity, the square root of x approaches infinity, and so this approaches 4 times infinity, which approaches infinity. And so we would say that this a sub n diverges. Because it does not approach a specific number. Let's consider the next example. A sub n is 4n minus 3 over 3n plus 4. Again, what I'll do is think of the function f of x is 4x minus 3 over 3x plus 4, and I'll calculate the limit as x approaches infinity of that function, 4x minus 3 over 3x minus 4. Alright, well, that would give me an infinity over infinity. That's an indeterminate form. So using L'Hopital's rule, I can rewrite this as the limit as x approaches infinity of 4/3, which is 4/3. Since the limit of that function as x approaches infinity approaches a particular number, in this case 4/3, we say that a sub n converges to 4/3. And let's see some visual evidence of this. I'm going to use the calculator here. Let me bring up the calculator. I'll turn it on. And if we go into our mode, we can change the graph from function to sequence. So let me change it over to sequence mode. I hit enter to put it to sequence mode, and I'll hit enter a second time to save it. Now, if you go to your y equals screen, you see a new notation. It's got u1. All right, and so u is the pattern, and that's what we think of as our a sub n. All right, so I'm going to type in u sub 1 as 4 alpha n minus 3 divided by quantity 3 alpha n plus 4. All right, now let me go to my window. All right, I guess I have to hit enter here first to save it. Go to my window, and notice it has an n min and an n max. So n is starting at 1 and going to 10. Plot start is at 1. Plot step is by 1. It's going to increase by 1s. It's got my x min at negative 10 and x max at positive 10. Well, for x min, I'm going to start at 0, and for my x max, I'm going to go 1 past 10. I'm going to go to 11. Now, I'm expecting a sub n to converge to 4/3. So for my y min and y max, I'm going to have my y min start at 0 and my y max go to 2. And then my scale I'll leave at 1. And let me go ahead and graph it. All right, and so it's just plotting those points. So this point is at n equals 1. We can actually trace this, F3 to trace. And so n1, we get 0.142, that's 1/7. All right, and n, when n equals 2, we get 1/2. When n equals 3, when n equals 4, 5, 6, 7, 8, 9, 10. So when n equals 10, we're at 1.088. We're expecting this to converge to 4/3, so that's not very good evidence, because 4/3 is what? 1.3 repeating. All right, so let me adjust my window. Let me go back to my window, and let's take the n max out to 50, and let me then change my y max to 51, and let's regraph it. All right, so it's plotting all those points. All right, now let me go ahead and trace it, and let's move to the right a bit. Oops, sorry about that. Moving to the right, and let's look at those y values. 1.2. So when n equals 50, it's only to 1.279. All right, well, let's change it a little. Let's change the window again. Let's go out to 100. And let's set my x max now to 101 and see what happens. I'll regraph it. All right, I'll hit trace again, and I'll just type in, I'll type in 80 now to go all the way there. All right, so when n equals 80, we're at 1.3 roughly. And so when n equals 100, it's only to 1.305. So it takes a while, but eventually it's going to get to 4/3, 1.3 repeating. All right, let's consider a couple more examples of this. Does the sequence converge or diverge? We have a sub n is sine of n pi over 2. All right, so if you look at this one, so finding a limit on this one is difficult because, well, if you think about what's going to happen here, if n equals 1, we've got pi over 2, the sine of pi over 2 is 1. All right, so let's see, a sub n is 1. Would be the first term. If the second term of the sequence, if n equals 2, we'd have the sine of pi, which is 0. If n equals 3, we'd have the sine of 3 pi over 2, which is negative 1, 0, 1, 0, negative 1, 0. And it continues. So we see that this keeps on oscillating between 1, 0, and negative 1. And so as n approaches infinity, it's not getting closer to any specific number. And so this sequence diverges. What about a sub n is the natural log of n plus 1 over the natural log of n? Well, I can quickly write that using our rules for logarithms as the natural log of n plus 1 over n. And so now if I think of the function natural log of x plus 1 over x, and I calculate the limit as x approaches infinity of the natural log of x plus 1 over x. Well, since the natural log is a one-to-one function, I can bring the limit inside. So that would be the natural log of the limit of x plus 1 over x. And that would be x plus 1 over x, that would end up being 1. You could apply L'Hopital's rule there, and so that ends up being the natural log of 1, and the natural log of 1 approaches 0. And so this limit converges to 0. The sequence converges to 0. All right, consider now a sub n is negative 1 to the n plus 1 times n over n plus the square root of n. Now, one thing to be careful about here is you see this negative 1 to a power. Remember that what that causes is an alternating sequence. And so when we have an alternating sequence, what we want to use is one of those theorems that I mentioned earlier. And what we will do here is we'll instead evaluate we'll look at the limit as n approaches infinity of the absolute value of a sub n. And so the limit as n approaches infinity of the absolute value of a sub n would be the limit as n approaches infinity of, well, notice what's going to happen. That absolute value of a sub n, that's going to knock out that negative 1 to the power, because that's just going to that just keeps on going between negative 1 and 1. And so under absolute, that goes away. And so we'd now just be looking at n over n plus the square root of n. All right, so let's think of that in terms of x. Limit x approaches infinity of x over x plus the square root of x. And that would be infinity over infinity, and so that is an indeterminate form. We apply L'Hopital's rule and rewrite this as the limit with x approaching infinity of 1 over 1 plus 1 over 2 root x. And now as x approaches infinity, that would approach 1 over 1 plus 0, right? Because we'd have 2 times infinity in a denominator. 1 divided by an infinity is 0, so we have 1 plus 0. And so this approaches 1. So what this tells us is the limit as n approaches infinity of absolute a sub n equals 1. Now, earlier we saw that in the theorem it said if limit as n approaches infinity of absolute a sub n equals 0, then limit n approaches infinity of a sub n is 0. But this is not 0, it's 1. Right, it's a 1. So what's happening here is this sequence keeps on alternating between numbers that are getting close to positive 1 and negative 1. Positive 1, negative 1. And so it's not getting closer and closer to a specific number. And so what we would have to say is that this sequence diverges. If that limit had ended up being 0, we would say that the sequence converges to 0. But since it didn't give us 0, the limit came back as 1, we would have to say that this diverges. Alright, this one's a difficult one. Here we're asked about a sub n is negative 3 to the n over n factorial. Alright, so like I did in the previous exercise, I'm going to think of the limit as n approaches infinity of absolute a sub n. Not a to the nth, sorry, a sub n. Because I see that negative 3 to the n, right? And so that's just going to keep on alternating between positives and negatives. So under absolute, this would be the limit as n approaches infinity of 3 to the n over n factorial. Now, we don't know how to find the derivative of an n factorial, or an x factorial for that matter. So L'Hopital's rule is not going to be of any use to us here. All right, so what I'm going to do is we're going to use a different kind of argument here. So let's assume that n is large. So for large values of n, we know that the nth term is going to look like this. We would have 3 times 3 times 3 times 3 times 3 times 3. And there would be n 3's, right? There are n 3's. The denominator would be n factorial. So that's 1 times 2 times 3 times 4 times n minus 1 times n. Now this is clearly greater than 0. Right? It's clearly a positive number. But what we want to do is we want to try to make it less than some other number. So here's what we're going to do. We're going to kind of break this up. Notice I can rewrite this big fraction as 3 over 1 times 3 over 2 times 3 over 3 times 3 over 4 times 3 over 5 times 3 over n minus 1 times 3 over n. Now again, this is greater than 0. But now, let's look at these terms. Let's look at each of these terms to the third term, or the third, I should say, factor. The third factor and beyond. 3 over 3, well, that term's equal to, or factor is equal to 1. The 3 over 4 is less than 1. The 3 over 5 is less than 1. Each of these factors is going to be less than 1. The 3 over n minus 1 is also less than 1. And we'll keep the other factors. We'll keep the 3 over 1, the 3 over 2, and the 3 over n. And so now what we can say is, since all of those other factors in the middle are equal to, or less than or equal to 1, then what we can say is 0 is less than, now this whole thing was the a sub nth term for a large n, and what we can say is that the a sub nth term must be less than or equal to 3 times 3 times 3, 27, over 1 times 2 times n, 2n. Since all of those other factors are less than or equal to 1, this is a result that we can get. So now, if we sort of think about the squeeze theorem, we can clearly see that the limit as n approaches infinity of 27 over 2n is 0. So by squeeze theorem, which you saw back in a Calculus 1 course, the limit as n approaches infinity of absolute a sub n is 0, and therefore a sub n converges to 0. All right, let's look at a few others here. These are all very closely related. They're all some base to the nth power. So 5 to the n, well, if we were to list the terms, we would have, what, 5, 25, 125, 625. Does this appear to be converging to a specific number? No, this diverges. Whereas here we have 0.2, well, that's 1/5. And so we would have, what, 1/5, 1/25, 1 over 125, 1 over 625. Does this appear to be converging? Yes, this appears to be converging to 0. These numbers keep on getting smaller and smaller, right? So this converges, and in fact to 0. Negative 1.3 to the n, well, that's what, just negative 1 to the n times 1.3 to the n. So the negative 1 to the n, well, that's going to keep on alternating, but 1.3 to the n is going to keep on getting larger and larger, just like 5 to the n did. And so what we're going to keep on getting is, a positive large number, then a negative large number, and a positive large and a negative large. This is going to diverge. But if we have negative 3/4 to the n, this is going to be negative 1 to the n times 3/4 to the n. And 3/4 to the n, if you just sort of think about it, the 4 is going to grow larger than, 4 to the n is going to grow faster than 3 to the n, and so this limit as n approaches 0, as n approaches infinity, of 3/4 to the n is going to approach 0. And so this a sub n will converge to 0. So a conclusion. the sequence set containing r to the n is convergent for r is between -1 and 1, including the 1, and divergent for all other values. Also, the limit as n approaches infinity of r to the n is 0 if n is between -1, if r is between -1 and 1, not including the 1, and the limit of r sub n is 1 if r equals 1. All right, so if we see a sequence that's of the form r to the n, then we can easily say whether it converges or diverges just by looking at the r. So now that we have some understanding of the convergence or divergence of a sequence, let's talk about a few more definitions that we want to be aware of. We say a sequence can be increasing or decreasing. All right, and so we say a sequence is increasing if basically the nth term is less than the n plus first term. All right, and it's decreasing if the nth term is greater than the n plus first term, and for all n greater than or equal to 1. If a sequence is increasing or decreasing, we say it's monotonic. A sequence can be bounded above or below. We can say it's bounded above if all of the terms of the sequence are less than or equal to some specific number m, and it's bounded below if all of the terms of the sequence are greater than or equal to some specific number m. If a sequence is bounded above and below, we say it is a bounded sequence. All right, so consider the sequence a sub n is 1 over 5 to the n. We want to know, is the sequence increasing, decreasing, or not monotonic? Is the sequence bounded? Well, we can easily see that that's 1/5 to the n. And so we've noticed already that this is a converging sequence, and it converges to 0, in fact. But are we sure that it's increasing or decreasing? One way to determine this is to consider the function. Let's consider the function f of x is 1/5 to the x. And let's calculate the derivative. F prime of x is 1/5 to the x times the natural log of 1/5. So we notice that, well, 1/5 to the x is greater than 0, and the natural log of 1/5 is a negative number that's less than 0. So what that tells me is f prime of x is less than 0, since I'd have a positive number times a negative number. F prime of x is less than 0 for all x. And so what that tells me is, since the derivative is always negative, f of x is decreasing for all x. And so then what that tells me is, since the function is decreasing for all x, the sequence is decreasing. Is the sequence bounded? Well, we know that's decreasing, and a sub 1 is 1/5. We also know that the limit as n approaches infinity of a sub n is 0. And so we would say that this sequence is bounded. Specifically, a sub n is greater than 0 and less than or equal to 1/5. So the sequence is decreasing and is bounded by 0 and 1/5. Is the sequence increasing, decreasing, or not monotonic? Is the sequence bounded? Let's now consider a sub n is 3n plus 4 over 2n plus 5. Right? If you were to list out a few terms of the sequence, right, that would give you the set containing, if n is 1, you'd get 7 over 7, that's 1. If n is 2, you'd end up with 10 over 9, so that's slightly more than 1. That appears to be increasing. If n is 2, you would get 13 over 11. That, I think that's greater than 10 over 9. And then you'd get, what, 16 over 13 and 19 over 15, etc. So these appear to be getting larger. This appears to be an increasing sequence. All right, so let's actually use some calculus to figure this out. Let's consider the function 3x plus 4 over 2x plus 5. Let's calculate the derivative using the quotient rule. Let's see, I'd have 2x plus 5 by 3 minus 3x plus 4 by 2 over 2x plus 5 squared. And let's see, that is 6x plus 15 minus 6x plus 8. So that's 7 over 2x plus 5 squared. Now notice the denominator is always, it can be 0 if x is negative 5/2, but for positive values of x it's always positive. And 7 is always positive, and so this is always greater than 0. So f prime of x is greater than 0, so then f of x is increasing for all, we can at least say for all x greater than 0. All right, there is that one issue when x is, negative 2/5, negative 5/2. All right, but at least for positive x, it's increasing. And so that's fine, because we're only concerned about n equals 1, n equals 2. We're only concerned about positive n. So what we can then say is a sub n is increasing. Is it bounded? Well, we know that a sub 1 is 1. We figured that out already. What about the limit as n approaches infinity of a sub n? Well, looking at the lead coefficients, 3 and 2, it appears, and we could apply L'Hopital's rule to the function with x approaching infinity, the limit as n approaches infinity of a sub n is 3/2. And so then we would say that a sub n is bounded. It's bounded on the bottom by 1 and on the top by 3/2. Now, we would say it's greater, we have the or equal to for the 1 because the first term is equal to 1, but the sequence will never actually equal, no term in the sequence will ever actually equal 3/2. They'll approach 3/2 and get close to it, but never actually equal 3/2. Is the sequence increasing, decreasing, or not monotonic? Is the sequence bounded? And here we have a sub n is sine of n pi over 2. And I think we described this sequence earlier. We saw that a sub n could be written as the set containing, if n equals 1, the sine of pi over 2 is 1. It would be 1, 0, negative 1, 0, 1, 0, negative 1, 0, etc. So is this increasing, decreasing, or not monotonic? Well, just looking at this sequence, we see that it keeps on jumping, right? It's decreasing, then increasing, then decreasing, then increasing. This is not monotonic. Right? Because it keeps on changing signs. However, it is bounded. In fact, a sub n can clearly only be between -1 and 1. So it is a bounded sequence, but it's not monotonic. All right, that concludes the presentation for this section.